Good morning. This is just a quick recap of the very end of our lecture on Chapter 2. Last week, we had two claim evidence reasoning statements. The first one was really contending with significant figures and making sense of addition or subtraction, multiplication or division. And if we think about this, right, we had a least number of decimal places for addition or subtraction, and we had a least number of significant figures for multiplication or division. And we're really combining these two. And so we're going back to ask that question in terms of, what does this measurement actually represent, right? How accurate could I really be? And so because I have one significant figure for the number 400, that's really going to be what drives my significant figures for my calculation. So I can determine what the number would be if I used a calculator without significant figures. But with significant figures, my answer is 8 times 10 to the 2 centimeters, because in the multiplication step, 400 has only one significant figure and no decimals. So that's the most accurate that I can be. The second claim evidence reasoning statement really had to do with the reaction between sodium metal, Na, and chlorine gas, Cl2, to produce sodium chloride, table salt, or NaCl. This illustrates the law of conservation of matter. We start and end with 19.6 grams of matter. And this is useful because a claim evidence reasoning statement allows us to draw a conclusion, that's our claim, and then support that claim with evidence. And our reasoning is really the way we connect the pieces of evidence together. We're going to be practicing making these claim evidence reasoning statements throughout Chem 110. But the idea is you're going to become adept or skilled at drawing a conclusion from information and then showing how your data backs that up. The other piece that we're going to continue to talk about as we explore Chapter 2 are models. And so a good example of an atomic model is what we're going to use to make sense of protons, neutrons, and electrons in an atom. So the actual size of these objects is 10 to the negative 15th, or 10 to the negative 18th, or 10 to the negative 10th meters. Incredibly small, so small that we would never be able to see them unaided with our eyes. So we're going to propose a model. A model is a representation that allows us to make sense of something that we might not otherwise be able to make sense of. And so for our model, we propose that a proton is going to be represented with a 10 centimeter, roughly, apple. Now we know that protons and neutrons are different, so I'm going to propose that our neutron is a 10 centimeter orange. You might have proposed something else. As long as it's consistent with the relative size of an apple, that would be great. So you could have said, for example, a pear. The electron is much, much smaller, though, than either the apple or the orange. And so we're going to represent that with 1 millimeter, or a speck of sand. And if we take all of that together and we think about how big that would be at scale, then our atom would be 10 kilometers, or 6.2 miles, or the width of Nantucket Island. And so it's useful for us to think about how our models have benefits. In this case, the benefit is we can see an apple, or we can see an orange, and we can see, right, their size with respect to, say, for example, a grain of sand. Right? But their limitation is, when we scale this up, it's actually pretty difficult to see 10 kilometers. You'd have to have a really clear day. So this model is something that's helpful for us. And as we move forward, it's a useful point of reference. The other thing that we need to be thinking about specifically when it comes to our atomic models is anions and cations. These are ions. So they're when charge comes into play. So when does charge come into play? Well, if I have a neutral atom, that's what I see in the center. It has 6 protons, 6 neutrons, and 6 electrons. And with your keen observation skills, you're going to notice that the number of protons and the number of neutrons isn't changing. What's changing is the number of electrons. So if I lose an electron, if I go from 6 electrons to 5 electrons, I'm going to form a cation. Whereas if I go from 6 electrons to 7 electrons, where I gain an electron, I'm going to form an anion. So the big idea here is that when an atom loses electrons, its charge is then positive. We call it a cation. When an atom gains electrons, its charge is then negative, and we call it an anion. So it's useful to know the difference between anions and cations because we're going to start to think about how these molecules behave. The last piece of information that we really need here is The types of chemical formulas. So we're going to have three that we're going to wrangle with so far. We have the empirical formula, which is the ratio of elements in a compound, but it's important this is the relative or simplest ratio. We have the molecular formula. This is the actual number of atoms of each element in a molecule. And then we have the structural formula. This is the actual atoms and their connectivity, so the way that they're connected together. So these three types of formulas are what we're going to use as we start to study these compounds in more detail. But before we do that, I want to draw us back to our reading and make some connections. So we're in chapter 2. This is 2.3, Atomic Structure and Symbolism. And the reason why I think it's important to start thinking about metacognitive strategies when you're reading is because you can draw out some of this information to set yourself up for success in class. So, for example, in the reading, they pose the following model. If the nucleus were the size of a blueberry, then the atom would be about the size of a football stadium. Think about that. Right? In our initial model, we were saying that a proton would be the size of an apple, a neutron would be the size of an orange. Well, here they're saying all of the protons and neutrons together are the size of a blueberry. So our model is a little bit smaller, in this case in the text, than the original model we proposed. But look at this. The atom would still be the size of a football stadium. Now, a football stadium is a little bit smaller than 10 kilometers, but it's at least a scale that I would be able to see. So maybe this is a model that helps me conceptualize the relative size and scale of an atom. Now, the other thing that might be worth thinking about for us, right, is charge. And so I gave an example here of the following sentence where a proton has a mass of 1.0073 AMU and a charge of 1 plus. And a neutron is slightly heavier with a mass of 1.0087 and a charge of 0. And it's going to be neutral. And then the electron has a charge of 1 minus and is a much lighter particle with a mass of about 0.00055 AMUs, which this was really interesting to me. It would take 1,800 electrons to equal the mass of one proton. So electrons are a lot smaller than protons. But what was here necessary for me is I had to do a little bit of wrangling with the text because I couldn't remember off the top of my head what an atomic mass unit actually meant. So that happens. It's not uncommon for you to be reading something in a text and then have to go and see if you can find out more information about that somewhere else. And that's one of the reasons why office hours and the CLC or time in discussion are so valuable. I gave you an example here of something that I highlighted because you simply have to know it. It's really important that we know the unit charge associated with electrons, protons, and neutrons. You are going to need to know that an electron has a -1 charge, just like you'll need to know that a proton has a +1 charge. That's how we assemble our nucleus. And then the other piece of this that I think is really useful is the way that we can interact with a periodic table. So in this case, a periodic table provides us really 3 pieces of information. The atomic number is the number of protons. The mass number is the number of protons plus the number of neutrons. So if I subtract Z from A, then I get the number of neutrons. So those are 2 of the 3 important pieces that I need to know. Then the atomic charge would be the number of protons minus the number of electrons. So that's what allows me to determine whether or not I have ions. There are a couple of examples in the text that I thought were particularly useful. So if I have a neutral sodium atom where Z is equal to 11, so that's my atomic number that's equal to 11, it has 11 electrons. If this atom were to lose 1 electron, then it becomes a cation with a +1 charge. So 11 minus 10 is +1. In this case, it's really important that I pay attention to the signs. If I looked at another example, a neutral oxygen atom where Z is equal to 8, and it has 8 electrons, and if it gains 2 electrons, then it becomes an anion with a 2 negative charge. 8 minus 10 gives me 2 negative. So this starts to give you a sense of how we can make sense of the charge or what ions we're forming in a molecule. I thought, this example of iodine was a really interesting one. I wasn't familiar with the condition called goiter, and so this was something that I read and found really interesting. But the last piece that I want us to take a look at is starting to think about chemical symbols. We're going to spend some time on Monday in class when we start to take a look at chapter 2, really digging into chemical symbols and chemical formulas. So the rest of chapter 2 is something that's really important for you. I hope you have a chance to check it out, and I will see you in class soon. Thanks again for your time. Have a great day. We'll catch you later.